Okay, so we've been reduction exists for single-threaded programs in functional languages. We saw in OpenMP how it can be used to create multi-threaded programs in a declarative language. So we are now going to go towards distributed programs. Okay, so let me just tie this with something we did very early in the course. We said that we are talking about the course on distributed systems, and we said we're going to assume that we are starting with non-distributed existing single-thread programs. If you want high-performance computation, we divided computations into two classes, high performance and consistency based. So we said, well, we can go to first multi-threaded programs that are non-distributed. And from that, we can go to distributed programs. And these programs themselves can have threads in them. And we can go to such programs directly from our non-distributed existing single thread program, or we can migrate from here. So we've seen this journey in many ways, and we were with OpenMP at this part of the journey, and we want to go and see some design pattern to make programs such as this. Okay. You guys have made programs like distributed programs in your assignments, and in your A3, you used a variation of the design pattern I'm going to talk about, but inspired by the design pattern I'm going to talk about today. Okay, and that was for high performance. For consistency, that was a separate design pattern, and in fact, we saw certain specific algorithms there. So if you want to go to distributed programs for high performance, we can just start with OpenMP. In OpenMP, all of input goes to some master thread in a single process. So these are threads and these are processes. And it splits. So what it does is OpenMP assumes that we have a loop, okay, and it goes and splits the iterations of the loop among multiple threads. Okay, and so we'll call each of them a partial reducer. So the idea is to reduce the problem to smaller problems. And the problem given to these threads are partially reduced. And we can just extend this idea by having the master thread give the work to a partial reducer thread in another process. Okay. And if we can have some kind of distributed shared memory, then this can work very effortlessly. Okay. So this is one way to go to a distributed context. So we have partial local reduction and partial remote reduction. Yeah, and you've seen something like this in your A3. And then the results can go back to the master, and the master can then do the final reduction. Okay. So the master now becomes a reducer, and it does the final reduction. Okay. And then out comes the output. Okay. So we could use this architecture. And people have proposed this to be the distributed variation of OpenMP. But MAPREDUCE that we are talking about is a very different beast. Okay. In fact, people think there's nothing to compare with OpenMP there. But I'm going to try to show you that there is some abstraction that combines them, and I'm going to show how they differ. So we'll see the connections. Okay. So to motivate why MAPREDUCE is so different from OpenMP, distributed OpenMP, I have to bring out the problems. And there are two problems. First, when you have really big data, okay, and we don't go big data computing that we see today, and MAPREDUCE is meant for such computations, there are efficiency problems. Okay, so you can always do everything in one thread, in one process, but we are trying to improve performance. So performance would not, has issues when data are very large. Okay, that's one problem. Second, we might be gathering data from geographically dispersed sites all over the world. Okay, so the canonical problem is that we have words from all over the world, and we're trying to see how often each word occurs so that we can do some natural language processing. So, given these two, so So given that we have geographically dispersed sites, and given that data can be big, what are the problems with this architecture that you see in front of you? Okay, let's try to answer this question first. And if we can answer this question, we are a big way towards understanding why we need MapReduce. So there are two issues. Chris mentioned that if data are far away, then there might be errors in transferring the data to the central process. Even if there are no errors, there might be a communication cost in transferring the data to one process. Okay, and in fact, the more the errors, the more the communication cost, because you have to go and send duplicates. So that's one issue. Then Chris also mentioned that, look, the splitting cost could be high as you go and split this data into different reducers. But I said, look, the splitting cost is proportional to the number of threads. So that's not so much of an issue. But the fact is that there's only one thread doing the splitting, which may not be so costly, but there's only one thread doing the final merging. And more importantly, the whole data must be processed by one process. And so if the working set of that process doesn't fit in memory, then this can become a bottleneck. So that's what I meant when I said, think about the fact that everything is being done by a central process. So this is a very, while there's some distribution here, this fork join scheme is good for medium-sized data maybe, but not for really, really, really large data. Okay? So we want to somehow get rid of these two problems. So the fork join model requires input and data to start and end at the for loop of one process thread. Okay, so that particular loop is the entry point, and we do some processing before it, and we do some processing after it, and then the iterations of the loop are parallelized. So which is inconsistent with big data for the reasons I mentioned earlier, which are written down here. So MapReduce provides a comparator for fork join loop-based reduction. Okay, so in OpenMP, we see many things. We see sections, we see parallel constructs without having nothing to do with loops, but we're going to focus on reduction and go and see how we can do reduction in a different way. Okay, so that's what MapReduce is doing. Okay, so it's a comparator, but it's not entirely different from it because the word reduce is here, and we saw reduce here too. So I want to go and join or unite the reduces. So let's remind us what reduction is. We saw that through example, that we had a list of numbers to go and sum up. We broke up the lists into sublists, and the sublists were summed up by partial reducers, and that the sums of the sublists were themselves a list that were then summed up by the final reducer. Okay. And we modeled these list summations as binary operations. And we saw that in distributed OpenMP, we basically split some data into among partial reducers, some of which could execute in the same process, some could execute in different processes. So again, the dark boxes are processes, and these white boxes are threads. So you split in one process. You can do the reduction in multiple processes. So that's good. Okay? We want to do something like that even in our, and that's where you get distribution from. Okay? But then if you're doing the final reduce again in one process. So all data have to fit in this process when they're input. They all have to fit in this process when they're output. And some computation has to occur here to merge, and some computation has to occur here too. So that seems like a natural way to do things based on what we studied so far. So is there an alternative to this, really, that allows reductions to occur in parallel? And what MapReduce does, that's the goal. We don't know quite how it does that, but we distribute the split. Okay? We distribute the reductions also. So some splitting can occur in one process, some splitting can occur in another process. Each process can go and input different data. Okay, so the input data can be divided into units, and each process can take different units. Each process can take one of the units, so different processes can take different units. Okay, and then they don't have to go and merge the outputs. Outputs go to the final reduction is done by different processes, which go and produce independent outputs. So there are some independent inputs, and out come some independent outputs. Okay. Now the set of independent outputs might consist of only one output. So in which case we are reducing this problem to OpenMP essentially, and the set of inputs can consist of only one input. So again, this can subsume the OpenMP situation. What it allows is when input can be distributed and when output can be distributed, then these processings can occur in different processes. In different processes. Okay, so that's a key idea here. Okay. And it's not as if everything is distributed. After the split, we talk of some final reduction, but there can be some partial reduction done in the same process. We can use multiple threads here. Okay, so and this is an inter-process. This is an intra-process split, and then the intra-process splitters can then go and do an inter-process split and go to different reducers. Okay, so we see an intra-process split here, then an inter-process split where different splitters go and send data to different reducers. Okay, so it's not as if this output phase is completely independent of the input phase, and the output these processes can output independently, and they can get input from different processes, and there can be some relationship between the outputs of different splitters. Okay, so we are getting there. So when we were doing an intra-process split, then the basis for splitting was a loop, and the splitting was done by system. Now we could control it. We could say, is it, is this the step size? Is something else a step size? Are we going to dynamic split, guided split, static split? We gave it some parameters, but the splitting code was provided by the system. And if we gave it no parameters, then it used defaults. So the splitting could be completely automatic. Okay, that's what happened in OpenMP. The reduction, on the other hand, we wanted OpenMP to be independent of what's going on in the loop. So it made no assumptions. It made an assumption that there was a binary operation being executed, but didn't make any assumption about the binary operation that was being executed. Okay, the binary operation had to follow some constraints. It had to commute. It had to be associative. So that was assumed, but the exact binary. Okay. So I'm going to argue that this can still be done in MAPREDUCE with the goals and the architecture I've shown so far, but this cannot be done by MAPREDUCE. Okay, we have to do a programmer-based split, defined split. Okay, and this is a subtle question. Let's see whether you guys can try to figure out why that's the case. Maybe it's not so subtle based on what I've written before the split. So why can OpenMP-based split not be used? That's one question. That should be easier question to answer. And then what can be the basis for splitting? Okay, so that's the question. So one difference is, this was the key here, loop-based split. So the basis for splitting was the index variable used, the step size it had, the limit, and those were the parameters given to process iteration. And we said we can replace process iteration that we wrote by a process iteration the system has. Okay. Whereas here now in MAPREDUCE, the data do not arrive at a loop. Okay, so here the data arrive at a loop. Here the data don't arrive at a loop; they just are there, and they are then sent to different processes. Okay, so typically what happens is they say in MAPREDUCE, processes go to the data rather than data going to the process. So Chris said that, look, there might be errors when we transfer data from one location to the other. So what we'll do is essentially transfer the process to the data location. Hopefully there won't be errors there, or the process program might already exist there. So we don't have these errors, and more importantly, we don't have the data transfer costs. Okay? So since data does not already live before the loop before it's split, it must be done based on file lines. Okay, so it doesn't make too many assumptions about what the file lines contain, except that it's a bunch of text. Okay, each line has a bunch of text in it, comma separated text. So by themselves, these files have little information that the system can use to do the split automatically. Okay, so the split must be done by the program. Okay, so there are two things I'm saying here. One, the split is not loop based; it's data based. Okay, and second, um, because it is data based, it must be done by the program. Okay. So the picture that I showed you is getting more complete. The programmer must go and split the data. Okay. And again, this is, since it's data-based and not iteration-based, it is making assumptions that there is some data to split. And while it's splitting the data, the same function that splits can also go and massage the data somewhat. It can go and do some computation on the data before it goes and gives it to the reducers. Okay, it is doing some processing, so let it do whatever it feels like before it reduces, before it goes and splits. Okay, that's called the map function. So we're not just talking the split function now, we're talking of a map function, which is compute and split, both combined together. Okay. And the data from these reducers, which is distributed, this goes to from one set of distributed processes to another set of distributed processes. Okay. And within these processes, it gets assigned to certain threads. Okay, so you can actually have multiple reduced threads here, multiple reduced threads here. I didn't show that here. So going from one set of distributed processes to another set is not really splitting, but a shuffle. Okay, so the thing that I was calling as an inter-process split, its technical term in MAPREDUCE is shuffle. Okay, so we are getting nearer and nearer what MAPREDUCE does. Okay, this is the architecture. So the key ideas are: we assume data fits in a set of input files other than a single process. Okay, so these files can be distributed, so we can have large amounts of data. So different processes get different portions of the files. The same file can be distributed to multiple processes, or multiple files can be given to one process. So there's arbitrary mapping between files and processes. Okay. And it is data-based and programmer-defined division. And the work is combined not by one process, but multiple processes who directly write output files rather than sending them to one process. Okay. So the output consists of a set of output files, which could consist of just one file or even one entry in the end. So OpenMP versus MapReduce. I'm repeating a few things just to make sure they sink in. So fork join model, starting at a for loop, distributed sites, okay, with the shuffling rather than concentration of the data into one process. So there's no merging. And the reason is that this is inconsistent with big data, and this is consistent with big data. This has a bottleneck. This doesn't have bottleneck. So this is loop-based division, and here we have data-based division. Now the nice thing about this, so the green lines tend to be the good things and the red lines tend to be the bad things. This is independent of any data structure. It just says you have a loop. Okay? It doesn't care whether your data structure is a collection, it's a bean, it is a hash table, whatever. This is tied to a data structure, and when we were doing OpenMP, we were thinking of arrays. Maybe that's the right data structure to have, but it is not bound to a loop. It's not trying to process a loop and do some intelligent stuff on it, intelligent processing on it. So there's no need, if you're using an existing language, to have a precompiler. Okay, so precompiler is a pain because by the time it gets compiled, the source code has changed, and when you're debugging, the debugger doesn't know about the mapping from the um, precompiled stuff to the compiled stuff, from the input of precompiler to the output of the precompiler. So precompilers are have problems. Okay, so this is independent of any language. Okay, and precompiler. This is OpenMP has different implementations for different languages. So the concepts are independent of any language, but the implementations are dependent on the language. So if we are going to be dependent on its data structure, we have to figure out what set of data structures should MapReduce support. So the external data structure is a file of text lines. Okay, so we have to worry about the reduction. What does reduction involve? The reduction involves basically key value pairs. Um, Reduction involves taking a sequence of key value pairs and converting them into a single key value. Okay, so since we're talking about key values, we're talking really of a map. Okay? The final output is a map. And the input can also be considered a map, which maps input line numbers to where the line numbers are the keys. So let's talk about map as a data structure. It chooses a map rather than an array, which we might have thought of given our OpenMP problems, or a list, which is a sequence, or a set, which has got no order, or just a simple int. Okay, so think about why, if we are to choose only one data structure. If you want to choose multiple data structures, then you can support all of them. But suppose we constrain ourselves to one data structure. Why map and not these data structures? What is so special about map? And this is really a programming language question before it is a distributed computing question. Okay, programming language designers have also been obsessed with the map, even though initial languages like Fortran and Pascal and Mesa didn't have maps. There were many languages that were obsessed with maps, and the map is not a fundamental data structure in Java, but there are languages in which it's a fundamental data structure, and there are reasons for doing that. And think of a map as a table, or so. So think about why map and not these other data structures, and think of one data structure being able to simulate another data structure. Okay, so let's go and make this a programming language question first. Okay, so can simulate bean. Beans are what? Property names and values. Okay, so property names can be keys and values can be the values associated with properties. Collection, as Chris mentioned, array list, we can go and just make the indices be keys. And set, we can just, we know that in fact a hash set is implemented using a hash map. Okay? So we just assume that the keys are associated with unique values. And in fact, you can think of and int can be simulated, as I mentioned, using a single hash table with a single key and value, where the key doesn't matter. Okay? So and think of relational database systems. They're supposed to keep the data of different language. They're supposed to keep all persistent data. The data might have started from an array. It might have started from a bean. It might have started from a collection. And you're supposed to, when you save it on disk, put it in a table. So there must be something about tables that allows you to simulate all these in-memory data structures. So that's another intuition behind why map is such a fundamental data structure. Okay? And like I said, some of the early languages did not have maps, but way back when I first did my AI course, there was a language called Snowball, and it had basically strings and tables. And Snowball by itself didn't make it very far. In fact, Snowball was a competitor to Lisp. They were both AI languages. So Lisp was a functional and AI language, and that was more popular among certain communities. But my first AI program, actually, I did both of them together, I think, in the same semester. But my more convincing program was Snowball. I'd essentially written an equivalent of something called ELIZA that that is like, uh, you guys might have heard of it, as a conversational agent with no intelligence in it. So, so it had only tables and strings. Okay, and then two of my favorite researchers, a guy called Chris Fraser at Bell Labs and Hansen at Princeton, created a language called Easy, and they argued that Easy was a language that could simulate, that could subsume existing programming languages, can also subsume OS data structures. So a directory was simply a bunch of nested tables. Okay? So a table or a map is a very fundamental data structure. Because if you want to choose one, it makes sense just from these high-level arguments why you should choose a map. So, and now you can see why the word map is used here, because you're essentially, the map is used in two different ways. You're creating a map, key values for a map, and you're also mapping input to something else. So it's sort of both things. But here's an issue. We can't just do arbitrary things on the map data structure. Okay, so I argued that maps are very good data structure uh, for programming in general. Okay, if we are to choose one data structure, we should use maps. Um, but when we're doing distributed computing, we have to go and constrain the way maps are going to be used. Okay? And that constraint comes from our architecture here. We don't want a bottleneck if we can help it. Okay? So we should be able to do computations on different parts of data without considering other parts. That's the key here. If we have to go and do these processings independently, and if our division is based on data, then some parts of data we should be able to compute on without looking at what has been done to other parts of the data. In our OpenMP case, we had a final merging phase where we could look at all the dependencies among the various parts of the data and create a value out of that. Create one value or a sequence of values or a bunch of values. Create a map, an int, whatever. Here we're doing things in a distributed fashion. So given that we have a map, here's the question, and what can be the basis for dividing independent parts of data in a map? Okay, and that basis, once we have that basis, then we can define what the constraints are. So given we are working with maps, key values, what can be the basis for deciding, hey, you process this part of the data, and you process this part of the data that were produced by the map functions. Okay, so the map functions produce some data. They got some data, they produce some data. That data have to be split, and they can be split among these reducers that are partial reducers or final reducers. So the question is, what is the basis for doing the split here and doing the split here, given that these splits are supposed to be independent of each other, especially the last final split is supposed to be independent of each other. So that's a long question. It was a very short answer. Let's go and see. So as Chris said, one process could handle a set of keys. Another process could handle another set of keys. Okay, that is the partitioning. And a particular process could handle only one key or a set of keys. But the set of keys in different processes should not overlap. Okay, so the basic idea is that the computations involving values associated with a single key do not depend in any way on the computations done on values associated with a different key. If that is a constraint, then indeed we can do what Chris said, that we can go and have different processes handle different disjoint sets of keys. Okay? So that is a restriction. We are not doing arbitrary computations. We're doing computations where this property holds true. Okay, so we'll create our maps, key value pairs in such a way, given a problem, we'll create our key value pairs in such a way that this constraint is followed. Okay, so we're getting nearer and nearer the MAPREDUCE. And what I'm doing is I'm trying to derive MAPREDUCE from a set of first principles, a set of goals, rather than saying, here's an API, it's useful, guys, learn it, you'll be able to do important tasks fast using this API. I'm trying to show that there's something fundamental about MAPREDUCE, um, and these fundamental properties can be derived from some practical goals. Okay? So that's the splitting. When we come to reduction, so far we've seen how we deviated from OpenMP, and now we are going to go and unite with OpenMP. Okay? So our reduction process is very similar. Again, we assume, operations and with this kind of structure. But what's happening here is we are talking about how different values associated with the same key can be combined into a single value to be associated with that key. Okay, so this is telling you what are the properties of the operations you might apply to the sequence of values associated with the key. Okay, so when we were looking at our OpenMP problems, we were always thinking of a sequence of values, an array. Okay, in our examples. Now think of that array being a set of values or a sequence of values. It's going to be a set actually that are associated with the same key. Okay, and you can have multiple instances of this kind of reduction happening for different keys. Okay? So assume reduction operation replaces a set of values of type T associated with the key with a single value of type T using some binary operation. Logically, a binary operation is actually a unary operation. Sorry, it's actually a n-ary operation. So it could be unary, binary. The operation we'll define will take a sequence of values or a set of values, and that those could be 2, 1. It won't matter so much, but think of there being logically a binary operation. And if it's logically a binary operation, then it should commute and be associative because we're going to do them in different orders in different things. Okay, so the reduction properties are very similar, okay, except that we're doing multiple reductions independently, with having to do with different lists associated with different keys. So we've got a lot of about the constraints that MAPREDUCE imposes. We know quite a lot about how it differs from OpenMP. Let's talk about the difference in the process used to develop a solution. Okay. In OpenMP, you write a problem from scratch. Okay, in fact, you've got a solution already that is single-threaded, and you say, OpenMP, here are some comments I put on my loops, make it multi-threaded. Okay. So there's no data structure provided to you. There are no constraints on what data structures you use. You write the problem from scratch. In MAPREDUCE, you have a data structure that you need that is a logical data structure, and you go and transform that into a map. Okay, so if you're dealing with a sequence, you will go and convert each index into a key. So in one case, you're transforming to another data structure, and then letting the MAPREDUCE framework work. And in one case, you're writing the problem from scratch. Okay. Now, this idea of writing from scratch or transforming is more general than just OpenMP versus MAPREDUCE. It's something you might have seen in computer science before also. Okay, that you had two alternatives. You can do something from scratch, or you can transform this into another problem. And what I want to do is think about something, think more abstractly about computer science, and see whether you can think of situations in which you did this and situations in which you did this. And you did this a lot. Even you did 110, you did this. Okay, but where did you do this? So if you've done 455, I guess is the course, then think of 455. Or if you've done the algorithms course, think of the algorithm course. And maybe even in operating systems, you might have gone and done something like this. Okay, so let's try to sort of take a step back and unite this subject with even more remote subjects. Okay, so proving from scratch, Okay, so I don't know whether you did this in 455 or not, but you can try to prove the halting problem from scratch. And Leo mentioned NP complete and NP hard problems. And traveling salesman actually is one of the NP hard problems, but the most fundamental problem that I studied when I studied this subject decades ago was the SAT problem. So you can try to prove that from scratch. Okay, and I never liked those proofs because they were long. Okay, I like these kind of proofs. Okay, so if you want to prove that two programs, so by the way, you might want to prove that two programs are equivalent. So for instance, I might write a solution to your A7 and then tell some program, hey, prove that my solution is equivalent to your solutions, and that way we can grade the programs, your programs. As it turns out, if I could do that, I could solve the halting problem. Okay, so I have basically I can map the halting problem into this program equivalence problem, and that implies that if I can do the program equivalence problem, then I can also do the halting problem. Okay, so these kind of problems were very neat. You know, they were small problems, they required insights, so I enjoyed doing those myself. Okay, similarly, Leo forgot how to prove the traveling salesman problem, but typically what you do is you convert you show that if you could do the traveling salesman problem in polynomial time, then you could do the SAT problem in polynomial time. Okay? So you do that kind of reduction. So I'm trying to say that, you know, the kind of, sometimes you just, you know, this gives you constraints. You have to think of the problem you're mapping it to, and so you're constrained. Okay, because you're constrained, you have fewer choices. So I love the solutions because they seem you know, natural, given there are very few alternatives paths to take. Here there are more paths to take. Okay, so I just wanted to give you a flavor of what kind of stuff we will see in the next half an hour, 1 hour, half an hour, hopefully, when we go and see how to go and do the use MAPREDUCE. Okay, and what's nice about this is that transforming one problem to the other is also called reducing. So it's really cool if we can go and do our reduction, our primary reduction using a secondary reduction where we've transformed one data structure to another data structure. Okay, and that transformation is the mapping task. Okay, so I've looked at a lot of the philosophy behind MAPREDUCE. Let's look at it in more details. So we have distributed input, and there is some interprocess input splitting. So this gets split into different processes. Again, these ovals are different processes. This oval I'm going to expand. So this is a bigger oval than this one. But these processes will be called mappers. Okay, and they're called mappers, but they'll do many things. And we'll see what they do in this big circle. Okay, so this is important. Processes can go to data rather than data going to processes. And that's one reason, one rationale for splitting. So you might say that, oh, this input will go to this local process, this input will go to this local process, and that's one basis for splitting. Another basis could be just load balancing. Okay? That we want some of the input to go here, some of the input to go here, and all of this input can occur in one site. So this might be, if you are in a data center, all these machines are near the input, so we just do load balancing. On the other hand, if you've got some data from Duke here, some data from UNC, maybe we send it to two UNC processes, one Duke process. Okay, so that can be a basis also for splitting. Then we go and we can have multiple map process threads within a process. Okay, so somewhere here the system goes and says, okay, these are the data that are meant for my process. I'm going to create so many mapping threads. So if you can do mapping in different processes, surely we can do mapping in different threads too. And then we go and map, we get the input, we generate key values based on some computation, and then we can do some partial reduction in our own process, okay, which involves intra-process shuffling. Okay. So some data from both of these map processes can go to this reducer. Some data from both of these mappers can go to this thread. And again, like I mentioned, it is key-based reduction. Okay, it's key-based splitting is key-based reduction. And then we have additional processes, and we call these processes reducers. Again, one processor will blow up, one processor will not blow up. Okay, so even though this process is doing mapping and partial reduction, we'll call it the mapper process. Okay. This is the reducer process, and it doesn't do any mapping, but it does and there is some inter-process shuffling that goes on. So some data from this mapping process will go to this particular process. So this process will get data from both processes, and so will this process. And then there is some intra-process shuffling. We don't have to do the reduction all in one thread. So we'll have multiple threads doing the reduction. Okay. So we finally do the key-based final reduction, and then we have a distributed output. What does distributed output mean? Think of each process creating a separate file. Okay, and think of all of those files being in a single directory. That directory has distributed files. So that directory stands for the whole distributed output. So that's what I mean by distributed output. Okay. So, what function you use to go and split the data among reducers, and what function you use to, so as we talked about, a particular reducer can handle multiple keys. Okay. As long as the sets are disjoint, we are fine. Okay. So all we want is for the sets to be disjoint. They can use different criteria to decide which set of keys a particular reducer reduces. So here's a question. I have some partial reduction, I have some final reduction. So some things you do for optimization, some steps you do for correctness. Okay. So think about final reduction and partial reduction. Are they both done for correctness? Are they both done for given that there has been some mapping that has already occurred? Are they both done for performance or both done for optimization? So think about that next. That'll help us understand even more. So is partial reduction an optional optimization? Is final reduction an optional optimization? These are my two questions. Oops. I went and had a student discussion on the wrong slide. Yeah, I hope I don't delete the slide later. So the final reduction is important to combine data from different processes. So this is not an optional step. Partial reduction, if we don't do the combination here, it will be done here. So this is purely to reduce the work at the other end that we're doing. Okay, so this particular step is optional optimization, and this is a required step. Given the data have been distributed, okay, we do need the work to go to different reducers. We do need the data from different mappers to be combined by the appropriate reducer, so that the appropriate function can be computed. Okay, so we could have these masters send data directly to the reducer. So this mapper could send data to this reducer, this mapper could send data to this reducer, and we needn't have gone through this stage because we need to combine the values. Okay, we have seen all the principles. Let us do some real problems now. And I'm going to do the classic problem I talked about earlier. You have words from all over the world. People have been writing prose, and we want to see how frequently a word occurs. Okay, this is a problem you've solved in your A1, A2, A3. Okay. So you know what the algorithm is like. Now the question is, how can we do this using MAPREDUCE? And I will just give you the solution here. And once you see the solution here, hopefully you can go and do other problems in a similar fashion. Okay. So let's look at the input. The input is a bunch of lines, bunch of files, and assume that each file has a sequence of lines, and these lines have got line numbers and these numbers are unique across files. Okay, so think of the entire input being a bunch of lines, and then each file containing a subsequence of that sequence. Okay, so this particular file has 1, followed by the two words that occur, two words, the and a. This has line 2 with a. Okay, so these words might have been gathered from Scarborough. These might have been gathered from Chapel Hill. They're both in one line, and this might have been these words might have been collected from California, for instance. Okay. Now this is the input. So what we have to do, if you remember, is that we go and take each word and convert that into a key value pair by making the word the key and the value 1. Okay, if you remember that from A1, A2, A3, that's what you did. So that's what it does. So, and I showed that these two boxes appeared concurrently. So I could have one thread in this particular process handle line 1. I could have another thread handle line 2. So these two threads could go and compute this key value pair concurrently. Okay. And then the thread that's processing line 1 can then go and compute this key value pair A1. Okay. Similarly, two different threads can process these two lines and compute these two key value pairs concurrently. Okay, so I've got the key value pairs. Now I have to do a reduction in the same fashion you guys did reduction in your assignments. Okay. So we have the same key associated with multiple values. One here, the same key associated with multiple values. So this is the sequence of values that have been produced so far by all these mappers. This is another sequence of values, and these two sequences have to be converted into one value. Okay. So we do some we do some local partial reduction. So our partial reducer gets a sequence of key value pairs. It gets the 1. So it says, okay, my final key value pair is the 1. This particular reducer also gets its own the 1. Says, okay, that's the value I will output if I get no other pairs. It gets A1. It says that's my final value. Then it gets another A1. It says, oh, let me go and change the value here. So it becomes A2. Okay. Similarly, this one gets AND1, and that's all it gets. So that's its value. Now we have to go and do we have to combine these two those. Okay. So we have to go and send both of these key value pairs to a single reducing process and ultimately to a single reducing thread. Okay. So it goes to the thread that's handling those. So does this the one. It goes to the same thread. That thread says, okay, let me add up these two guys, and it produces the 2. Okay. A2 goes here, and 1 goes here, and we get A2 and 1. Okay, so you see this thing working, and this particular process produces this file. This process produces this file, and these two files are in one directory. So we've got all our work. Okay. So this is the classic problem. If you understood how this goes, in theory, you haven't seen how you write the program, but you understand the underlying principles going in this algorithm. Okay. So let's look at some code. And we're writing Java here. You could write it in any language, but the MAPREDUCE framework that I'm talking about is tied to Java. So if you remember, when you were doing A3 or A2, I forget, I gave you many interfaces that you had to implement, and I gave you links to interfaces in MAPREDUCE that our interface was mimicking or just copying exactly. Okay, so since you were writing in Java, it made sense to just point you to some Java API. Okay, so that's the code. That's code. It's not too much of code here. And this is the mapping function. So as I told you that the splitting or mapping is also programmer defined. So this is equivalent to the process iteration thing that we wrote first for OpenMP. And we are doing this map. Okay. So let's see what's going on here. we are going to be creating keys, right? We're going to be taking input files and creating key value pairs. Okay, we're going to create key value pairs by creating a key and associating that with value. The value we will be always putting is the value 1. Okay, and notice we have this programmer has said ONE 1. Okay, this is good programming. Hasn't put the number 1. Somewhere here we have the value 1 declared as a final variable. Okay, so for those of you who've done 401 with me, I don't know how Ram has done 401 with me, and so has Akshay. You know how much I've harped on magic, not having magic numbers, and you probably would consider this excessive. And you might have thought only somebody like me would not consider this excessive, but you can see that this programmer was following good principles. Okay. While we're on that subject, let me just say something else. So I've had a student actually look at successful GitHub projects, and we're trying to see whether these GitHub projects follow the style rules that that people think are good and that I've asked my 401 students to follow. And we found that by and large, they all do follow these rules. Okay? So if you guys go out in the real world, it is important to write code that is self-explanatory. So let's see whether we really understand this code or not. Okay, so we see that we've got this constant 1. We have this key value 1. Now we're going to have multiple keys with input, but just to make sure that we don't allocate multiple times, this programmer creates one text object and just goes and sets it to different values. Okay, so it's setting it to the next token it gets from some tokenizer. Okay, so what's the tokenizer getting its input from? From a line. Okay, so basically what's happening is this map function gets as input a line number, which is the key, and the line associated with that line number. Okay, this line number it totally ignores. That's what we did on our problem solution. Okay, this is the one, and it's going to replace. It's going to have its own key, which is going to be this value. Okay, so it's going to take this value, break it up into its words. This is a line, and go through each word. And for each word, it's going to go and assign that string to the word text object here, set that to this particular token, and then say output.collect word, comma 1. Okay? This output is not something that's returned by this map function. Output just happens to be a sequence that has been input as a parameter. Okay? So what you're getting is a sequence and you're adding to that sequence. Okay? And I kept talking in my class about a serializer assignment that I didn't even dare to give to you guys because you were so out of time. But something very similar happens in the serializer also. Okay? That when you create a serialized object, you get an input parameter that you write into, and different serializers write into the same sequence. Okay? So you see how this is faithfully doing what I abstractly showed in the previous slide. Mapper transforms input into reducible output. The output happens to be this collection of key value pairs. Okay. So method fills in a passed output collection rather than returning one. And key is equal to line number, value equals to line in the input. Okay. And we have reused the key variable here. Okay, so that we don't have to allocate this text again and again. And this makes me happy. This is a named constant. We didn't just say. And if had we gone and said new int writable 1 each time, maybe that's the reason why this person did it. Then we'd be allocating this value again and again too. So I think that may be the real reason that he's trying to make sure that the allocation, he or she has tried to make sure that this allocation is done only once. So let's compare this with OpenMP. We have a loop here. Okay. OpenMP is okay. Let's go and see what I'm trying to say here. So two things. Firstly, we are giving to the infrastructure a map method. We are not giving it a loop. Okay. and it's distributing the map method among different threads. Okay, so it goes and says, hey, this thread, go and handle this line. Hey, another thread, go and handle another line. Okay, so this is uh, this particular function is being you know the method is being used to parallelize the task. Okay, and we are working with infrastructure provided types. Okay, you see this output collector, which is parameterized. You see long writable. So we have, this is the most important constraining type, that we are limited to producing key value pairs. Okay, and they're parameterized by the type of the key and the value. Okay, but otherwise, it's an infrastructure provided uh, type. So that's the difference between OpenMP and MapReduce. Okay? But let's go and look at this loop here. Could we imagine, conceptually, this may not be practical, using OpenMP to parallelize it? Can you imagine just putting some tokens before this while loop and saying, let's have OpenMP and MapReduce work together, rather than thinking of them as alternatives? Wouldn't it be so cool if we can go and combine their functionality together? Okay, so this programmer didn't do it because they might not have known how to use OpenMP, or they might have thought it can't be used. Okay, who knows? But since we know more, or we have a different goal in mind right now, let's go and see whether we can, this loop could be parallelized using OpenMP. Think about that. OpenMP assumptions. So we noticed that we could parallelize this particular loop. Okay, it has a variable being initialized, it has a termination condition and step, but we could not parallelize this even though they were equivalent, because the header did not have enough information that it needs to do the splitting. Okay. So this works, this doesn't work, because OpenMP requires a header that gives it the information necessary. Okay. So we could not, in fact, parallelize that loop that I showed you. But we could go conceptually and put the strings in one line into an array, and then write a for loop of the kind. So when we did this, we could go and do has more tokens, put all those tokens into an array. So write one loop to do that, and then write another loop that is actually parallelized by OpenMP. Okay. So conceptually, we could have done it this way. Okay. Now writing that initial loop to go and put this into an array would take space and time, so it may not be worth it. But I just wanted to show you that logically this can be done. And if this particular computation that this loop does is very complex, then it might even be worth it. Okay, but in our examples, that won't be the case. Okay, you've seen the code, you've seen examples. Now you guys have to make your brains work. Okay. So tell me now how I should do this problem. The problem is I have collected temperatures from various parts of the world. Okay. This is and you know, in today's world with the virus going around, you can imagine collecting statistics of a different kind from different locations. But here, let's just go and talk of temperatures. So you have two readings in location A of the temperatures. Okay, one reading says a 70, another reading says a 60. You have one reading of B in this file. So it says the temperature at city B has been noted as 55. Another file that also goes and has a temperature recorded about B. So this might be recorded in Durham. This might be recorded in here, and B might stand for North Carolina. Okay, and we have another temperature reading here. I want to go and produce the minimum temperature for each city. So the minimum temperature in city A is 60. The minimum temperature in city B is 55. Okay. So I'd like to do this all using MAPREDUCE. So we need to figure out, given these input lines, what key value pairs does the mapper produce? And given a set of key value pairs produced for the mapper, given a key and a bunch of values associated with the key, what function does the reducer go and execute to produce the final value? Okay, and this is your simplest problem, guys, so hopefully you guys will get this. So what are the map and reduce functions? So mapper ignores this line number, okay, and uses city as key and temperature as value, as Leo mentioned and Andrew wanted to mention. Okay, so we've got A70, A60, B55, B70. And Leo, you use too many words. So what we have basically is a key with a sequence of values. And we want to go and apply some function to the sequence of values. And we apply the min function. And you define the min function, that's good. But that's the function you use. So earlier you used the sum function. Now we use the min function. Okay. So A70 and A60, the min function gives you 60. We have only one temperature, so 55. So this is where it's not really binary. 70, 90, A60 and A90, B55 and B70, we get A60 and B55, and that's the result. Okay. So this is also a very popular example in the MapReduce literature. Okay. So this was supposed to be easy. Let's go to something a little harder. And given that you have done A1, A2, A3, maybe this can be done. So sum is the canonical example used by OPENMP. Okay, word count is the canonical example used by MapReduce. OPENMP guys never talk about word count, and MapReduce guys never talk about sum. Okay, but just to sort of understand the differences between these two, I try to go and do both problems using both systems. So we saw at the end of our OPENMP lecture how to do MapReduce, how to do word count using OPENMP. And so now let's try to see how we can do sum using MapReduce. So here are my lines. Okay, my lines have got these numbers. Okay, so previously our lines had pairs of values. Now we have numbers. So we have on line 1 number 5, line 2 number 3, line number 3, number 3, 4. We have two numbers, 2 and 1. Okay, so we are supposed to go and produce some key value pairs. What key value pairs do we produce? Okay, what are the map and reduce functions? Okay, so as Andrew mentioned and as we did in our assignment, mapper ignores position. Okay, so we really don't care about the line numbers, and maps each input into some constant, something, we'll call it S, and that int. So we have S5, S3, S3, S2, S1, and then we go and combine these values partially, and then we go and combine these values finally. Okay, so we now produce only one data item. Okay, we've got S14. Okay, so this is not using all the capabilities of MapReduce, but we see at least how the problem can be done using MapReduce. Okay, so since all these values depend on each other, then we have to go and map them to a single key. Okay, here's a problem that neither MapReduce people nor OpenMP people ever do. When we did OpenMP, we did the rounding problem where we wanted to take a sequence of values and get the rounded values from them. So this doesn't quote unquote naturally map to the MapReduce problem, but to understand the MapReduce framework better, let's go and consider this edge case. Okay? So we have these values here, which are real numbers, floats, and we want to take each float here and get back its rounded value. Okay, so this 5.2 becomes 5, that 3.3 becomes 3, 3.4 becomes 3, 2.2 becomes 2. Okay, it's rounding it, right? Yeah, and 1.3 becomes 1. Okay, now we don't care about the key values as long as we can get these values output, we are happy. Okay. So not a practical real world problem. I mean, rounding is important, but like I said, it's not something that either of those mechanisms tries to solve. But we can solve it using this framework. So let's go and see what a map function might be and what a key function, round function might, sorry, what a reduce function might be. Okay, so mapper converts each position comma float to position round int. Okay, and that position is a row and a column number. So think of each of these being a row with each entry being a column. So 1.15, 2.13, 3.13, 4.12, and 4.21. And reducer gets a single value for each key, so it just outputs it, and there you get the output. Okay. Okay. And then we can sort it by key to go and get the original sequence. Okay, Chris, I expect you to answer this question very quickly. So now I want to do rounding, but sum of the rounds. Okay, so I want to sum up 5 plus 3 plus 3 plus 2 plus 1. So Chris or anybody else, tell me what the map and the reduce function. Okay, so as Chris said, mappers convert each float to S comma round float. Okay, and then we basically do what we did for sum. Okay. Okay, guys, I know it's the end, but if you can understand this, we are talking of an application that Facebook has for MapReduce. That here's an algorithm it runs every night to find common friends of people. Okay, so what it does is it gets from all over the world people usernames and their friends. So it got the data for A, and A has two friends only, B and C. Typically, it will be some hundreds or thousands of people. So this file has the friends of A and C. Okay, A and C both refer to B. B is not in this file. B is another file. I hope that stuff comes here, but and we want to go and produce, in the end, we want to produce the common friends of each pair of users. So this is the common friends of AB, and this is the common friends of AC. Okay, so we want to produce this data, and here's the okay. So I think what I'm doing in this slide is proposing a particular key, and you have to tell me why that key doesn't work. Okay, so what if I make the key be the user and the value be a sequence? The value can be any type, right? Any Java type. So let's say that value is an array list consisting of all the friends. Okay, so we have A's friend, here's the key A and a sequence BC. Similarly, we have B here, sequence ACD, and C and AB. And now we could just go and intersect BC with ACD to figure out the common friends of A and B. Okay, and we can take intersections associated with different values. So I'm going to with intersections of values associated with these different keys. I'm arguing this is not the way to do it. Okay, and why does this kind of transformation of the problem violate MAPREDUCE constraints? Okay, that this is what you shouldn't be doing if you want to find common friends between two users. So if you want this output, this is not what you should use as a key. And if this is not what you should use as a key, what should be used as a key is the question. Okay, so for each map each S list to S comma list. Okay, where this list has got this greater than sign here to separate the username from the friends. I'm saying this is what you should do. And if you could do this, then what you need to do here is that given if you want to find the common friends between U1 and U2, go to a table, find the friends of U1, find the friends of U2, intersect them, and you will get the common friends. But I'm claiming that intersection cannot be done using a reduce function if this is your map function. So what property of MAPREDUCE disallows us from doing something like this? Why will this not work and what will? Okay, you guys figure this out. At the end of the day, you know that would be really cool. But at least you can answer this question, even if you can't figure out why it won't work or what should be the right answer. Just see why it won't work. Okay, so as Leo pointed out, the keys here and the keys here are different. And if somehow we are, we don't know what we're doing here, but somehow we are changing the keys. We are changing the keys that were produced here. So these keys that we are producing the output were never produced in the input. So if we can indeed transform the keys, then who knows, when you have multiple reducers, you might have multiple transformations here. So we can't predict what keys will be produced in the end if the keys that we produce are a function of the reducers. So put another way, we don't produce new keys in the output. We take values associated with the same key and go and combine them and store them with that key. We don't go and change the key. So reducers do not combine values associated with different keys. So must associate sets to be intersected with the same key. We do want intersection, but the values that are to be intersected must have the same key value. Okay? That is the, no pun intended, that is the key here. Okay? So what we'll do is the following. To find common friends of A and B, we must go and map A's friends and B's friends to the same key, which is a function of the usernames A and B. So let's look at example and let's look at the general algorithm. So what I do here is I say, I go and take, I know that A has the common friends, A has friends B and C. So I go and say that if I ever am given the key, so for A and B, if I ever have to go and intersect the friends of A and B, I will use the key AB. Okay, so I'm replacing this A with AB and saying, look, BC are the friends of A when A's friends have to be compared with B's friends. Okay. Similarly, BC are the friends of A if A's friends are to be compared with C friends. Okay. So for each S list F1, I map it to S dot F1, A dot B, and F1 to F1, Fn, S dot F2, F1 to Fn, and so forth. Okay, so the whole idea is that if I ever have to go and intersect, find the common friends of A and C, we will use the key AC. Okay, and then we go and process this line. Okay, so you might think that we can just say C dot A goes to AB. Okay, this dot should actually have occurred after A. Okay, and this should just be so there should be a dot here, and there shouldn't have been a dot here. Okay, C dot A goes to AB. But if we do C dot A here, then C dot A and A dot C are different. So we go and alphabetize these two guys. So I go and transform this into A dot C, comma AB. Okay, so now I'm processing C's friends, and I say if C is to be ever compared with C's friends have to be ever compared with A's friends, we will use the key not C dot A but A dot C. Okay, and similarly we say C dot B to AB. This is not in alphabetical order, so we'll go and make it B dot C associated with A dot B. Okay, so my animations that are hidden have had some errors, but this is what we end up doing. Okay. Similarly, we do BA. BA has the friends ACD. We make that AB, ACD. Okay. Similarly, we say BC is ACD and BD is ACD because we're taking each of these B with each of the friends, and that's alphabetically sorted. Now we can give it to our reducers. Okay. So reducer goes and takes these two keys with these two sets and goes and intersects BC with AB and produces B. Okay. Similarly, AB just goes to BC, BC goes to AB because there's no intersection. And again, there's nothing repeated here, so there's no intersection. Now we take AB.BC and AB.ACD, okay? And we go and have ACB, and this gets converted into AB, comma C. This just remains as AC, comma B, so we got the output we wanted. Okay. So this is what they say. I read. I'm not sure how reliable this is, but in a Stack Overflow post I read, this is apparently the algorithm Facebook runs every night to find common friends between users. Okay, so it doesn't just pick two users and say, okay, let me find your common friends. It runs the algorithm on all the users and all the sites and produces at the end the common friends of all pairs of users. Okay. So you've learned not only MapReduce as a practical thing, but you've also learned something about Facebook. Okay, we are done, guys, with the concepts. I want to finally tie this to your assignment. Okay. So your assignment was neither OpenMP nor MapReduce, and that was not my goal. You know, implementing both OpenMP and MapReduce is pretty difficult, and actually I made your task difficult in ways that MapReduce and OpenMP don't address. I wanted you guys to have practice with bounded buffer problem, practice creating threads. So what did we do? We took our input, gave it to a master thread. The master thread went and gave the work to the reducer threads, just as OpenMP does. Okay, and but we didn't have iterator. We didn't have a loop-based division. Okay, what we did was but we did have key value pairs being produced, and we went and put these key value pairs into a bounded buffer. Okay, I wanted to give you guys practice with bounded buffer. So it was basically a dynamic scheduling of OpenMP. Okay, except that it was not loop based, so it was a little bit more complicated. And then the reducers could go and give their task to distributed uh, um, threads. Okay, so this is how we got distribution, like MapReduce. Okay, so they also did partial remote reduction, and you could also have partial local reduction. Okay, so we got a bunch of values to go and reduce, and they were gotten from the bounded buffer, and they could be reduced here or they could be reduced here. And once reduction completed, the reducers then shuffle data among themselves, if you remember. Okay, so they now entered a new phase after the barrier phase, where they were shuffling data to each other, and they were using a shuffling function that that had the same signature as the shuffling function in MAPREDUCE, I believe. Okay. And the shuffling was based on keys. Okay. We used a very simple-minded key-based shuffling. And then after the shuffling, they went and did some final reduction based on what they were given. Okay, so they went and so these reducers shuffled the data to themselves, and then they went and processed those data, and that was the final reduction. And again, the final reduction could be done remotely or locally. Okay, so this work was given to a remote thread, and then finally, all the data were collected by a master thread. Okay, and out came the output. So you can see elements of both. And here's where the master process ended its join. So let's see our algorithm working with the example we did of word count. So in our problem, the end user input a bunch of tokens, and our goal was to go and count the number of times the token appeared. Right? So this sequence of tokens was given to a master thread, which produced key value pairs from this, and put each key and value in a bounded buffer to be consumed by a bunch of threads, which were the consumer threads here, the number of threads it had created. Okay, and as the MAPREDUCE function did, mapper did, each token was converted into a key value by making the token the key and the value. Okay. So these items are consumed in the order in which these consumers go and do the gets. So the first slave gets the first item, it gets the second item, the second thread gets the third item, the first thread gets the fourth item, and so forth. Okay. First thread sees a null, it says, okay, my list is complete, my input list is complete. Let me start producing output, and I will I will go and shuffle the output. Okay, so the output that I'll produce will not necessarily be consumed by me in the next phase. So these same threads become first partial reducers and then final reducers. So they have to shuffle their output to each other based on the keys. Okay, so it says, okay, the two is something I produce from these two the's by doing a summation. This is a partial reduction. It's to be consumed by me. A1 is to be consumed by the other thread, so I'll put it in its list of work, but that list is not finished. Okay. This particular thread finally gets down to seeing its null. It doesn't want to process the data on its own. So it goes and copies it and sends it by a remote method invocation to the client. The client takes this as input, and it starts through this particular thread. It goes and shuffles its data. So A1 and AN1 basically go to this particular thread's work. Okay. At this point, both threads will come out of the barrier and start processing their shuffled data. Okay, so this particular thread has only one piece of work to shuffle, to finally reduce, and this thread has 3 pieces of work. Okay, so this thread just simply goes and produces the 2 in the final output. It's got only one item. This thread, as again, is lazy, so it goes and gives the work to this client. The client goes and processes the list it had output earlier, and it goes and through this particular client produces the final output where the 2 A's have been combined by it, and the AND doesn't need to be combined. Okay, so you see here that there is some remote work. The remote work was done by copying first the initial list and then the final list to it. Okay, so one of these items in the final list was produced by this particular thread, so this particular item had to be copied back into the client. Okay. And finally, these outputs are merged together by the master and used to produce the final output. Okay, and the final output, of course, is the appearing twice, A appearing twice, and An appearing once. And I guess this slide should have gone with my previous slide, so I'll try to move the slide before I record. But this is telling you how the problem I did differed from what you guys did studied in OPENMP and MAPREDUCE. Okay. Okay, guys, 1 hour 41 minutes. I hope you thought you consider this worth it. Lots of text. I can let you guys read this when you're studying for your exam. If you ever want to use MapReduce, here's some tutorials. And I gave you some code, and that code was not the complete code. So if you this is just for reference, and it's for my reference too. But how to really configure things. Um, okay, and this is, like I said, full code. Okay, I'm glad a bunch of you showed up.